Welcome back to our journey through dynamic topology. In this session, we're going to explore a really beautiful and nuanced idea, local connectedness. Now, we already have a great handle on what it means for a whole set to be connected, right? But what happens when we zoom in? I mean, really zoom in. How does a set hold itself together at a microscopic level? Well, that's the big question we're going to answer today. So here's our game plan. We're going to kick things off with the core definition. Get that foundation solid. Then we'll unlock two really powerful equivalent ways to think about this concept. First, through something called open components, and then through regions. After that, we'll see how this property behaves in a special kind of space, a continuum. And finally, we'll bring it all home by tying all three perspectives together to see the full amazing picture. And this, right here, is the question that's going to drive our entire discussion. We spent a lot of time on connectedness as a global property. Can a set be broken into two separate pieces? But today, we're changing our perspective. We're zooming in. We're asking about the very texture of the space right around each and every point. Is it still holding together on that tiny local scale?
To answer that, we've got to start at the beginning, with the foundation. We need to nail down the formal definition because honestly, everything else we talk about today is going to build directly on top of this one core idea. Okay, let's break this down because it's super important. A set is locally connected at a single point, let's call it P, if it can pass a very specific test. Imagine you challenge me with any open set U that contains P. It doesn't matter how small you make it. My job is to find an even smaller, connected open set V that still has P inside it and fits completely within your U. If I can do that for any challenge you throw at me, at that point that it's locally connected there. And if this holds true for every single point in the set, then the whole set is locally connected. So what's the big deal here? How are these different? Well, a set can be one without being the other. And that's what makes it interesting. Think about a simple disk. It's connected, right? One whole piece. And no matter where you zoom in, it's still connected. So it's both. But now consider the famous Topologist sine curve. The whole thing is one single connected shape. But if you look at the points where that frantic curve meets the y-axis, you just can't find those nice, small, connected neighborhoods. Any tiny bubble you draw there will always catch infinitely many disconnected little slivers of the curve. So it's connected globally, but it fails the test for being connected locally. Okay, so we've got the definition. But, sometimes definitions can be a bit tricky to work with directly. So let's find a more powerful way to test for this property. This brings us to our first major equivalence, a theorem from Weibert's text that gives us a completely different but totally valid way to see things.
And here it is. A set M is locally connected. If and only if, for any open chunk you take out of M, its connected pieces, what we call its components, are themselves open. That if and only if is huge. It means these two conditions are logically identical. If one is true, the other has to be true. Let's prove it.
All right, let's walk through this proof together. First, we'll assume M is locally connected, and our goal is to show that its components have to be open. So we start with any open set U inside M, and let K be one of its connected components. Now pick any point P you want inside K. Since we're assuming M is locally connected, we know we can find a small connected open neighborhood of P that sits inside U. But here's the kicker. K is the biggest possible connected set in U that contains P. That means our little connected neighborhood has no choice. It must be completely contained inside K. And since we can do this for any point in K, it means every point in K has a little open bubble around it that's still inside K. And hey, that's literally the definition of an open set. So K is open. Done.
Now, let's go the other way. Let's assume that for any open set, its components are always open. We need to prove this forces M to be locally connected. Okay, so pick any point P and any open set UP around it. That intersection of M and UP is an open set in M. Now, let K be the connected component of the set that contains our point P. By our starting assumption, this component K has to be open. And just look at what we've got. We found an open, connected set, K, that contains P and is a subset of UP. That is precisely, word for word, the original definition of local connectedness. It works both ways. That was pretty cool, right? But we're not done yet. Let's build on that with a second, really powerful lens for looking at local connectedness. This time, we're going to tie it to the idea of a region, which, in topology, is just a fancy name for an open, connected set. At first glance, this might look almost exactly like the original definition, but it's stated a little more directly. It says local connectedness is the exact same thing as having this guarantee. For any point and any open neighborhood around it, you can always find a smaller region, a nice open connected bubble that still contains the point.
So, how do we prove this one? Well, the good news is the heavy lifting is already done. This first direction is a direct payoff from the theorem we just proved. Let's assume M is locally connected. Pick a point P and an open set up. Now think about the component K of the intersection of M and up that contains P. From our last proof, we know that because M is locally connected, this component K must be open. Well, a component is connected by its very definition, so K is an open connected set containing P inside up. That is, by definition, the region we were looking for. Simple as that.
And this just brilliantly illustrates the reverse logic. Now we assume we can always find such a region RP. Well, what is a region again? It's just an open and connected set. So our assumption is basically saying that for any point P and any open set UP around it, we can find an open connected set, our region RP, that sits inside UP. And that, well, that is a perfect match for our original definition of local connectedness. The equivalence is solid.
All right, we have a really solid toolkit now for identifying and thinking about locally connected sets. So let's put it to work. In this next section, we're going to see how this property behaves in a really important class of spaces called generalized continua. Now, this is a really fantastic result. It's telling us that for these special spaces, which are connected, compact, and locally compact, the property of local connectedness is, in a way, hereditary. If you take an open, connected piece, a region, out of the larger space, that piece inherits the property. It's locally connected all on its own. Okay, before we jump into the proof, let's just do a quick huddle and make sure we're all on the same page with the key players here. Our starting space is M, our locally connected generalized continuum. We're taking a region R out of it, which is just an open, connected subset. And our one goal is to prove that R is also locally connected. The proof starts out pretty simply. To show R is locally connected, we just need to satisfy that original definition. So we'll pick any old point P inside R, and any open set UP around P that's also inside R. Now here comes the first key insight. Because R is itself an open set in the bigger space M, our smaller open set UP is also considered open in M. That's a crucial first step. And this is where it all clicks into place. We can now use the fact that our big parent space, M, is locally connected. Since P is a point in M and UP is an open set in M, the definition guarantees we can find an even smaller connected open set, let's call it VP, that contains P and fits inside UP. And since UP is completely inside our region R, this connected set VP is also completely inside R. So think about it. We started with a point in R and an open set in R, and we found the required connected neighborhood inside it. The definition is satisfied. The region R is officially locally connected. Okay, let's pull everything together now. We've covered a lot of ground. In this final section, we're going to synthesize the three different, but totally equivalent ways we now have to understand what it means for a space to be locally connected.
This slide is really the whole story in a nutshell. We've built up three equivalent viewpoints. The main definition is maybe the most intuitive. Zoom in anywhere, and the space stays connected. The component property is more structural. It tells us that the connected pieces of open sets behave nicely. They don't have weird hidden boundaries. And the region property is super practical. It guarantees you can always find a nice connected bubble inside any larger bubble. These aren't three different ideas. They're three powerful, distinct tools, all measuring the exact same underlying topological property.
And that leaves us with one final tantalizing question to think about. We've now mastered what it means for a space to have this connected property at every single point locally. But what happens if this property isn't just present everywhere, but is somehow consistent and uniform across the whole space? That's the essence of something called property S and uniformly locally connected sets, and that is exactly where we're headed in our next session.